unlearning, which we are basically researching since past 3 years. Why machine unlearning is important, we will try to understand what are the different methods, what are the state-of-the-art method, and we will look at open challenges. So the title of the talk is Machine Unlearning and How Models Can Forget by Design. So to build up the tone of the lecture, and before I start, so I work largely on all these domains which are listed in these slides, like malware analysis, security of AI, adversarial machine learning, cyber threat intelligence, and also recently we are also having some footprints in large language models, attacks, and mitigation strategies. So why machine unlearning? Before that, to motivate you, there are privacy laws all around the world. Especially in Europe, we have the European GDPR laws, uh, which which has an article called as an Article 70, which says that if at all a user uh, is sharing data with some business organization, and in future the user finds that his or her data is sensitive, and if he wants the organization to forget the data, how it can be done. So the user have got all freedom to to demand the right to be forgotten. So we also have another very famous privacy regulation, especially in California, which is called as CCPA. So if you look largely across all different countries, so there are some or the other privacy protection bills, or let's say there is something that is related to privacy, which everybody is talking about. So in general, what is there in privacy law? So most of the privacy law talks about or addresses these concerns. So first one is right to access. So in right to access, what happens is a user like me can actually request the access of the personal data and inquire any organization about how my data is being handled or how the data is being used. The second one is right to data portability. So as an individual, I have a right to say that a company A who was using my data can transfer my data to some other company or some other service provider, let's say company B. So the whole authority or the power is actually held up with the individual. Then the next one is right to be informed, which means every individual must be informed that their data is going to be collected. For example, now we have seen that when we try to fill some form in some website or some application, they will say that their personal data will be used, will be gathered, maybe it would be gathered for some survey or for advertisement purpose. So we as an individual, we should know like how the data provide the model owners or how the business organizations will be using it. The next one is right to be information corrected, which means that every individual should be having a freedom for their data to be modified, altered, or updated whenever it is needed. For example, I change my workplace, I change my address. So I should be having the full freedom to update my data if some business organization is using my data. Then right to restrict information processing, which means that a user can say that, okay, you can collect my data, but the data should not be used for some advertisement or for some survey or some analytics. So it can be there in place, but through that data, extra knowledge should not be extracted. And the last but one is called as right to object, so which means right of the individual to stop processing for direct marketing. And something which I will be talking about today is the last one, which is called as right to be forgotten. But before that, if the data is basically modified or it has been captured by an attacker or adversary, then the user should be informed timely about the breach of the data. And then the right to be forgotten, which is basically the emphasis of the European General Data Protection Right, which emphasizes that every user can demand for the data erasure or data deletion. So, why machine unlearning? In a nutshell, when we talk about machine unlearning, there are certain regulations by different countries which demands data transparency for all the user. So, a user who is called as a data owner, if they are sharing their data, let us say to a business organization, and let's say they develop a machine learning model. So on one hand we have the user who is the data owner, and on the other side we have something called as the model developer. So there has to be complete transparency in data handling. Okay, so if we look at the most spoken data protection or privacy regulation, one is called as the European GDPR. It gives complete control of the personal data to the user, and also in the CCPA, which where a user have got the control of their personal data from the business that is collecting. So the summary of this slide is that all the regulations, they talk about transparency in data handling. So let's try to go a bit technical and try to understand what machine unlearning means. So before machine unlearning, if we try to understand machine learning in a layman's language, so if you look at the pipeline that happens, that is there in the machine learning, so we start with the collection of large amount of data. Then there is a phase where data pre-processing is done or data is transformed in some way, and this data is further partitioned into a training set, a validation set, and a test set. So we present this training set to any machine learning algorithm which tries to memorize the intrinsic patterns within the data, and then before deploying the model to some space, let's say cloud, what happens is this model is validated using a validation data, and finally we try to test the model on the unseen data during the inference time, which is with the test data. So if you look at this diagram and just forget about these two objects which are shown in the blue color as well as the gray color. So we have a complete data over here, and some part of the data is sensitive, which is shown by this gray color object, and something that is that one wants to preserve is called as the remaining data, or sometimes it is called as the preservation data, or sometimes retained data in some literature. So in an essence, we take the original data set which comprises of the remaining data as well as the sensitive data pertaining to a user, and we use this complete data in order to train a model, and let's say we build a model and call that model now as the original model. So what unlearning means is, from the original model we have to create a new model which is now called as an unlearned model, which will not have the information corresponding to this private data or or the sensitive data, which is called as the removed data. So in an essence, what we want to do is we start from the original data, and from this original data, we would like to remove by some mechanism, by some approach, the effect of this sensitive data to actually have a new model which is called as an unlearned model. Now, uh, this unlearned model should exhibit some qualities. So one of the quality is that if you give this removed data as an input to this unlearned model, or if you present this removed data to the unlearned model, the output probability or the prediction score corresponding to the sensitive data will be very low. It would be random, but it would be very low. It will not be zero, by which we will speak later. It should be very low. On the contrary, if you give this part of the data, which is called as the remaining data, to the unlearned model, the prediction score should be equivalent to what we have got in the original model. So, in an effect, what we want to achieve through machine unlearning is that the model utility on the remaining data should be same as the original model, but at the same time, the prediction probability for the sensitive data points, or the forget set or the unlearning set or the private set should be low, random low. Additionally, what we would like to have when we try to create an unlearned model is this model should exhibit the same quality as a model which has been created without the absence of the sensitive data point. So that means when we use the same model architecture and we train the model from scratch, which is called as the model, a model which is called as a retrained model, the performance of the unlearned model and the retrained model should be similar. Okay, so this is what is called as the this can be the way in which we summarize machine unlearning. And if we are further interested to learn to read about what is machine unlearning, you can actually go through the paper of machine unlearning solution and challenges, which appears in IEEE transaction on emerging topics in computational intelligence. So, having understood what is machine unlearning, what are the different types of machine unlearning? So, machine unlearning approaches are basically classified into two different categories. One is called as an exact unlearning, and the second one is called as an approximate unlearning approach. In an exact unlearning approach, what we try to do is the model developer's job is to physically remove the data point from the data store, so that whenever the end user presents the same data point to the model, what will happen? The model will show a very low confidence score corresponding to that data point. So, in an effect, through exact unlearning, we would like to remove completely the influence of the sensitive data from the model. So, in an effect, we can say that the model completely forgets the information about the data point. On the contrary, we have other class of algorithm or technique which is called as approximate unlearning. In approximate unlearning, the job of the model developer is to look at the internals of the models, which are basically the weights or which are the gradients, okay, or in summary we call it as the parameter space of the model, and then try to bring changes in the parameter space corresponding to these sensitive data points, or scrub the parameter space in such a way that the prediction corresponding to all sensitive data or the private set will be low, but at the same time the prediction score corresponding to the retained set or the preservation step should be as high as possible. So our question should be like, what is the need of an approximate unlearning technique? So today we are living in the world of generative AI, and we frequently use generating models like ChatGPT or Gemini, which have been basically trained by large volume of data that is available. So imagine that some end user who is using such LLMs creates a prompt and try to filter out some sensitive information corresponding to him or her, let's say the credit card information. Then if we want if that user wants forces the large language model to basically forget that data point, then imagine that the model has to be retrained from the complete volume of the data excluding the private data point, so which is computationally very expensive task. So as we know that like training or maybe retraining an LLM is computationally expensive, and it is not a sustainable solution also. So in such cases we can actually use approximate unlearning. Exact unlearning will not be a feasible solution or a realistic solution in case of LLMs. So it is an expensive task. So let us try to understand basically a couple of techniques which are very famous and which have been used or which have been modified by researchers. So they build over these techniques. So one of the technique is called as CISA, which comes from a very famous group of security of AI or machine learning security from that is from Nicholas Papernout. And this is one of the very good papers to read because it comes from the top security conference, which is IEEE Symposiums on Security and Privacy, which have been ranked A star in the computer security domain. So CISA as contains basically, if you look at this particular word, it contains four alphabet. So the first letter is S, which is called as sharding. So sharding means that take a huge amount of data set and divide the data set into some subsets. So we start with the data set and we partition the data set into some subset, and every subset is called as shard. Then second one is called as isolation, which means that you take one subset, you take a model which is called as a sub-model, you train this model with a specific shard. So which means that if I have a data set which is partitioned into 5 subset, so basically I have 5 shard, so I will be creating 5 sub-models. And the point to be understood over here is that if I take shard number 1 and shard number 2, the data points of shard number 1 will never participate in shard number 2 or vice versa. So that means each shard has got instances which are non-overlapping, so they are independent. So the sub-models that are created will also be created, will be trained in isolation. So the information of one sub-model will never be available with the other model. So that means what the first sub-model is memorizing, it will not be available with the other model. So that is called as training in isolation. The third point is called as slicing. So as we do in conventional learning process in machine learning, we take a data set, we divide data set into batches. So now here every shard is further divided into smaller set, and each set is called as slice. And finally what happens is like the output of all submodels are aggregated using certain aggregation function, maybe like majority voting or weighted averaging, and then eventually the final prediction is done. To summarize, so sharding means dividing the data into training data into multiple disjoint set, and take each disjoint set which is called as shard and train the separate model. Each submodels are trained independently so that the influence of one data point in a specific shard is not reflected to other. Then slicing means to further divide the shards into a smaller number of subsets. Then finally, aggregation. Each model is basically the output of each models are aggregated through certain techniques called as majority voting or averaging. So this can be diagrammatically understood through the next slide where we start with the data set. We divide it into some number of shards, as you can see here from shard 1 to shard n. And then each shard will be presented to a model. The model learns the pattern corresponding to the shard, and the output of the shard is basically aggregated, which would cause the final prediction of the data point. So, what is the beauty of CISA? The advantage of CISA is, let us say, the sensitive data point corresponding to a user is available in shard number 1. Then, what I have to do in that case, being a model developer, is to remove the data point from the specific slice and then only retrain the a particular submodel. So which means that submodel number 2 to L will be preserved as it is. Okay. So basically what is happening is it is not retraining things from scratch. Only the changes will be reflected in submodel 1 and remaining the remaining things will submodel will be preserved as it is. So that is the advantage. We don't retrain from the scratch. We just try to find out the data instance presence in a specific shard, and then we try to retrain that particular submodel, preserving the others as it is. So, CISA basically is unlearning a specific data point. So what we do is we basically try to retrain that specific model. So the only thing that we need to do is we just have to find out the last parameter space. Okay, then just forget the subsequent one. So which means that if I have 1 to 100 iteration, and let's say my data point is used at the 90th iteration, so basically I just preserve everything, all the parameters from 1 to 90th epoch, and whatever was memorized beyond 90, it just needs to be changed. So effectively we just have to modify the effect that is happening on last 10 iteration. So let us look at the performance of CISA in terms of the advantage and disadvantage. So the advantage is like it reduces computational cost and the time that is required for unlearning, because the training is happening onto a specific submodel where the data point is a participant of a shard. So we don't retrain the model from scratch. The second thing is, like, since we are using the aggregation function or the aggregator function, which is maybe an averaging or a weighted average uh, or maybe a majority voting. So what is happening that the majority of the information that is memorized by all other models from model number 2 to n is effectively contributing, because it has not changed. Only the change that has happened is only in model number 1. So it maintains the prediction accuracy by aggregating the knowledge of the submodels. Also, it is a flexible and scalable solution, because let us say that if we want to have some more data, let's say new evolving data that has to be added to our architecture, what we do is we create a new shard, we train a new submodel, and maybe pass the output to the aggregation function. So it can be used without compromising the overall performance of the model. But there are certain limitations. So the limitation is involved in the isolation component of the CISA. So as I said, uh, the data points that are there in the shards, they are non-overlapping, which means that the models, they don't carry any knowledge from the other models. So they are being trained independently. So this isolation itself is a problem. So the main limitation is like if you talk about the neural network architecture where there are multiple neurons and the information of one neuron is also taken into the consideration by other neuron in the subsequent layer. So in isolation, what is happening is like you are not allowing the next model to transfer its knowledge to the previous model or to other models. So in that case, the models are not learning complex patterns. So that is another problem. So an alternative problem is like CISA requires additional storage. So as I said, and if you remember what I said is like we have to keep a record of the parameters. So because if I want to remove any data point, memory from the model, I should have some set of the parameters that are already stored and the parameter corresponding to the private data or sensitive data point, it has to be removed. So we need to keep record of all the submodels and the parameters, so which is basically computationally expensive in case of large data store. And another thing is like the problem of isolated training, and since all models are trained in isolation, they are not sharing the information with each other, so it might affect on the generalization of the model. So the generalization of model might be degraded. So these are the problems that are with CISA, and if you are interested to further explore, I may point you to a paper on machine learning from the group of Nicholas Peppernout. So let us try to discuss another concept of unlearning, which comes from the approximate unlearning domain, and this work actually appeared in the top artificial intelligence conference, which is called as AAAI, and the title of the paper is called as Amnesic Machine Unlearning. So amnesic is basically a medical condition where a human subject tries to forget uh, some instances or some instance or an event that is happening in his or her life at a particular period of time. So basically, it's a condition, a medical condition, which we call as amnesia. So the idea of amnesia is this condition uh, or this knowledge has been mapped to the algorithmic side, and that technique is basically called as machine amnesic unlearning. So amnesic unlearning is effective when we want to remove focused data points from the model. So at this point of time, I would like to summarize two concepts. One is called as the class-wise unlearning. So in class-wise unlearning, the objective is to unlearn a specific class. So let's say there is a class called as dog, and there is a class called as cat. So in class-wise unlearning, the objective is to learn a specific class, let's say all images corresponding to the dog class has to be unlearned. On the contrary, if we talk about the instance-based unlearning, uh, or sample-based unlearning, the objective is to unlearn a specific data point. So, for example, a dog with the picture of a dog with an owner. Okay, so maybe the picture of a dog with an owner is a sensitive image, so that has to be unlearned. So amnesic unlearning is useful when we want to remove the focused data points. It is effective only on those cases, but if we want to use this technique for unlearning large amount of data, let's say a class, it will be a failure. So this technique is specifically created whenever we want to remove focus data points. So this in this technique, the model does not undergo complete retraining from scratch. Rather, the influence of these private data or sensitive data is removed. We will see how it can be done. And thus it is categorized, or it falls under a category of faster unlearning technique. So let's try to understand how amnesic unlearning can be developed. But before that, what happens in case of amnesic unlearning is the model owner keeps a record of some of the basic information. So the first information the model developer uh, would keep track of is the batches which consist or contains sensitive data points. So a batch which contains private data or sensitive data is termed as sensitive batches. So the model developer in this technique should keep track of examples that appears in sensitive batches. And so what the model developer has to do is like to record the parameters corresponding to every batch, because if a data point is present in a sensitive batch and if I want to remove the effect, so I have to do some changes in the parameter space like weights or gradient. So I have to scrub the influence of that particular parameter. So we have to keep track of the batches. So whenever an unlearning request arrives at a model, okay, so how this algorithm functions is it will try to find out a specific iteration, a specific batch, and an iteration when this private data has been used, and then effectively scrub off the influence of the parameters corresponding to that data point. So that is the way in which the amnesic unlearning is done. So let us try to summarize this step. So if we look at the traditional way of learning, we start with the randomly initialized weights corresponding to any model, let's say a deep learning model. And this randomly initialized parameters are represented by a symbol called as theta subscript of initial. And then we have some epochs, and then we also divide the entire data set into some number of batches. I just want to check maybe if to check whether I am audible, if there isn't any network issue. Can you hear me? Am I audible? Can somebody give me a feedback if I'm audible? Can you hear me?
Yes, sir, you are audible.
Yes, sir, you are audible.
Oh, okay, thank you. So then what we do is like in the training process, essentially what happens is there is a change in the parameter. So you start with the randomly initialized parameter, and then what happens eventually is that at every iteration there is a change in the parameter, and this changes happens in every iteration when the batch of data is passing through the flowing through the model. And so as we know that we pass the data, and the output of the model, at the output of the model, we try to actually compute the difference between the actual label and the prediction. So that difference is basically called as an error. So what we try to do is we backpropagate the error. So during the backpropagation, effectively we try to change the model parameters, which are essentially the weights and biases, until the loss is minimized or error is minimized. So we use different types of loss function like categorical cross entropy loss or cross entropy loss for binary or multi-class problems. So in an essence, we can summarize the training process mathematically like we would like to build a model M consisting of parameter theta, which actually starts with the randomly initialized parameter, and to this randomly initialized parameter we keep on adding the changes, which is represented over here with a single delta. So what essentially happens is like we start from the first epoch, we take the batches of data, we try to estimate the change, okay, and this change is estimated through the loss function during our back propagation, and then we keep adding it to the initial parameter, and eventually the model would converge after some sort of an iteration. And let us say our model is M, which is now memorizing the parameter as theta. Now, still we have not started unlearning. So how an amnesic unlearning happens? So in amnesic unlearning, there is a record that is kept corresponding to sensitive batches. And what is the definition of a sensitive batch? A sensitive batch is a batch that contains at least one data point which is flagged as sensitive, which is a private data point. So, what happens in amnesic unlearning is there is a collection of batch which is called as a sensitive batch represented by SV. Now, during training, what we would like to do during the unlearning process, what we would like to achieve is we would like to create a new model which is called as M dash, and this M dash model should not have the memory or knowledge corresponding to the the sensitive data points. So effectively what we would like to do is we would like to remove all sensitive data or sensitive batches or the knowledge about sensitive batches from the original model M to build a new model M dash. And I again recall that the definition of sensitive batch is a batch that contains sensitive data point. So essentially what we would like to do is from our original model, which is theta n, which we discussed in the previous slide, from that we would like to remove the effect of all parameters from the which is participating in the sensitive batch. So for example, let us say I have two batches. So what I will do is I will try to remove the influence of the model parameter corresponding to these two batches. But if you try to think like, let us say if you have 100 batches, and in out of these 100 batches there are only two sensitive batches, because we can assume that there are only two data points which are sensitive and they are spread across two different batches. So we are performing this subtraction operation only for two times. Imagine the case that this unlearning data points are spread across multiple batches. So which means like 100 batches are there, okay? And in 100 batches, let us say 50% of the batches are sensitive batches, because they contain sensitive data points. So we will repeat this step assuming 250 times. So this will basically perform aggressive changes in the model parameters. So this is what I would like to conclude at this point of time, is that MBSIC unlearning will be effective if and only if we would like to remove smaller number of data points, or it would be effective if we would like to perform instance-based unlearning. But it would miserably fail, this approach would miserably fail if we would like to perform class-wise unlearning, and this class is spread across different batches. Then in that case, we will be having many sensitive batches. So if we look at the performance and if we try to understand the positive part of MBSIC unlearning, it will perform very well if the number of sensitive batches are low, because the impact that is going to happen in the overall performance of the model will be minimal. So, to the summary, this will be effective if I would like to remove individual data point, or if I would like to protect the privacy of individual records. On the contrary, if the number of sensitive batches are larger, then as I said, there will be aggressive changes in the model parameters. So in that case, the utility of model or the fidelity of model will go down. So that means if you now present the preservation set to the unlearned model, the performance will be very would drop significantly, and in order to maintain the performance, what one could do is the model developer could perform some number of fine tuning with the preservation step in order to retain the utility of the model. So this is an additional step that is required. So what is the drawback? It also requires some storage. So there is extra storage. So if I want to unlearn, so there is a trade-off. Like I would need some extra storage in terms of maintaining the knowledge of the sensitive batches and the parameters that is corresponding to sensitive batch. So if the number of sensitive batches are less, then the storage requirement will be less. But on the contrary, if our data points are spread across multiple batches, so then we will have multiple sensitive batches. In that case, we have to keep track of the parameters of multiple batches, so we need an extra storage. So this is the problem with the MBSIC unlearning. So I would discuss now another approximate unlearning technique. So before approximate unlearning technique, which is using a concept called as knowledge distillation, I would just do a quick 101 on what knowledge distillation is and why it is used. So if you are further interested to explore about knowledge distillation, I would like to point to a wonderful paper by Geoffrey Hinton, which is called as Distilling the Knowledge in Neural Network, which is one of the seminal papers about knowledge distillation. So to summarize knowledge distillation in a very simple language is that we would have a larger model which is called as a teacher model, and from this larger model the objective is to create a small model which is called as a student model. So when I say larger model, the number of layers in the teacher model will be larger, the parameters are more, but so the whole objective is from the teacher model we would like to create a student model, and this student model's performance will be similar to that of the teacher model. So that is the whole objective. So we start with a big model. We would like to create a smaller model which is called as a student model, and this student model should perform equivalently to the teacher model. And we use this concept of knowledge distillation now for unlearning. So let's try to look what knowledge distillation means. So in knowledge distillation, you take the same input, you pass it through a complex model, which is called as a teacher model. At the same time, you pass it through the student model. So the architecture wise, these two models will differ, but the output layer of both the models are similar. So which means that the output that we get from the teacher model is a softmax. It's a collection of probability. And the output from the student model is also softmax, which is also a probability. So let us forget about what this T is. And then through this softmax, what we would like to find out is the soft labels from both this model. And if we say that the student model should perform equivalently to the teacher model, so the difference between the soft model obtained through the teacher model and the student model should be identical. So which means that I would like to solve a loss function over here such that the difference between the soft labels obtained from the teacher and the difference between the soft label obtained from the student should be as close as possible. So which means that the loss should be minimized, and this loss is called as the distillation loss. But at the same time, what we would try to do is we would try to solve another loss function which is called as the student loss. And what is the student loss? Is like we take the soft label, we copy the same soft label over here, and we would try to predict the class corresponding to the instance X, and then we already have the ground truth label corresponding to X, which is called as Y. So at the top here we have the prediction, we have the ground truth, and here we try to solve a loss function. So the difference between the prediction and the ground truth is minimized, and this loss function is called as the student loss. So in knowledge distillation, we try to create a total loss function, which is actually a component which contains two components. One is a distillation loss and another is a student loss, and basically they are weighted. So the total loss is the weighted, which will have some weights of the student loss plus some weights of the distillation loss. So this is called as knowledge distillation. So we would like to minimize both the losses. And effectively, if we find out if a model, if this particular model converges after minimizing these two loss function, we would say that the student model has distilled the knowledge from the teacher model. So you can imagine in the realistic scenario also, being a teacher, we can assume that a teacher is more knowledgeable, and by delivering the lecture, by teaching the student will distill the knowledge from the, not the complete knowledge, the part of the knowledge from the teacher. So why knowledge distillation was actually postulated? The knowledge distillation actually solves one of the important problem which is called as model completion. So the advantage of knowledge distillation is like we can create a small model which is called as a student model having the same accuracy as the teacher model, which if we have to use that teacher model, we require enough computational power. So the knowledge of the teacher model is transformed to the student model, and by doing so, we can use such models to be deployed into devices which is having less computational capacity and which are battery operated devices. So in terms of efficiency, the smaller model, they require less memory and processing, and thus they are effective for real-time applications. Also, knowledge distillation is beneficial in terms of scalability, so they are more scalable solutions, so they can be deployed into larger number of devices as they are small models, because the overall overhead in terms of cost and energy is basically low. And finally, it improves the generalization capability because it smooths the decision boundary by distilling the information from the teacher to student, and they are less prone to overfitting. So, as I said, in knowledge distillation, the student model actually it is trained with two loss functions. So, the first loss function is called as the cross entropy loss, which is basically shown here by a symbol L subscript of CE, and a distillation loss, which means that effectively we would like to uh, minimize the difference or probability distributions between the output of the teacher and the student model. So, and this distribution, this probability distribution, basically it is solved through KL divergence. So, so the first part is the cross entropy loss. So, where we would like to basically bring down the difference between the ground truth as well as the prediction. And the second one is the distillation loss, which is basically represented as LKD. So this is nothing but here we are trying to find out the KL loss. So we would try to bring the two output distributions from the student model and teacher model as close as possible. So the first part, as you can see here, is basically the softmax of the student model and the teacher model, and the softmax is basically divided by another constant, which is T, which is called as a temperature constant, and this is done in order to further smooth out the probability. So if you have a larger temperature value, you basically smooth the probability in a very higher sense. So this is basically used in an approximate unlearning technique, and this approximate unlearning technique is called as a two-stage retraining process that we will be discussing now. And this technique is called as two-stage retraining. So there will be two stages. So the first stage of this unlearning approach is based on creating certain data points which we want to unlearn with contrastive label. So contrastive label can be thought of a label which is a wrong label corresponding to a data point. So basically what we would like to do in this stage one, I will take a data point, I will assign it a contrastive label which is not its true label. Then the second point is like these sensitive data points which is now assigned with the contrastive labels would be forced to unlearn from the model, and when we do an unlearning in an approximate technique, we are trying to tweak the parameters of the model. We try to scrub the parameters of the model. So it might bring down the quality of the model. When I say quality of the model, it might bring down the performance corresponding to the retained set. Okay. So in order to avoid that, we would be applying the knowledge distillation in the sense that the knowledge of the preservation set will be passed on to a model, an unlearned model, so that the knowledge of the retained set is preserved on the unlearned model. So let us try to look how this approach can be implemented. So there are two stages. Again, to summarize, the first stage one is to build a contrastive label. Then you perform unlearning. The second stage is to pass on the knowledge of the preservation set or the retained set to the unlearned model. So let's look how it can be done. So what is contrastive label? The contrastive labels is like you start with the forget set and you relabel the forget instances or the sensitive data point with the new label, or it could be unknown. So in this example, let us say that I have a classification problem of classifying the images as apple or banana. So there is a class called as red apple, and let us say there is a class called as a green apple. And if I want to forget the instances corresponding to the green apple, what I will do is I will change the class label of the green apple from green apple to red apple. So what happens is in supervised learning, every data point is associated with the label, and we are basically teaching the model about this association. So basically during the training process, if we are trying to associate any data instance with a wrong label, so basically we are trying to remove the association that the model has done. So that is called as contrastive label. So let us try to understand how this contrastive labels can be created and what are the problems also associated with it. So before that, let us discuss about the unlearning requirement. The unlearning requirement is eventually to create a model which is called as an unlearned model. And when this unlearned model is presented with a forget set, the output corresponding to the unlearned model should be some random probabilities. I give an emphasis on the word called as random probability. So the confidence score corresponding to the forget set should be very low. It should not be equal to 0, but it should be random. So we would say that, so the requirement is that the confidence score or accuracy corresponding to the forget set should be low. So alternatively, what is also demanded is that the accuracy that is corresponding to the retained set or preservation set should be high. So we would have two objectives. One objective is for the forget set, the accuracy should be random or the output should be random, but it should be low. But at the same time, the confidence score or the accuracy for the preservation set should be high. So now the question that one should ask is why we are saying it should be random low probability. Why it could not be 0 for the forget set. The reason is that if the score corresponding to the forget set is 0, exactly 0, and if you imagine that this model is available in some cloud server or it is available as machine learning as a service, so an adversary can probe the model, and if he or she gets an output as 0, the adversary can guess that the specific data point might have been used for training. Okay, so this is a form of a membership inference attack, which means that the adversary would have got a clue about some data point whose output value or confidence score is 0. He or she would understand that specific data point might have been used for training. So that is why we would like to achieve random probability, but a low random probability instead of 0. So let's try to understand pictorially how this unlearning approach could be implemented. So on the left hand side, if you look here, we have a complete data set which contains two parts. One object which is colored in green, which is the data point that we would like to retain. Another data point which we would like to forget is, let us say, represented in this orange color object. So with these two subset, we basically train a model. Okay, so this is so the model remembers the information about the preservation set. Also, the model remembers the information corresponding to the private set or the sensitive data point. So which means like this sensitive data point, like there are 4 instances and their class label are purple, blue, and 2 red. So in stage 1, the objective is to create a new model which is called as a neutralized model. And how this neutralization is achieved is like you take the sensitive data points and you try to label all these sensitive data points with the contrastive label. You force the data points with a new label. So something like this. So the first thing what we have to do is to generate the contrastive label. So there should be some mechanism of generating the contrastive label. So which means that for all sensitive data point, you basically shuffle the labels. And then you take your original model and then you try to perform some unlearning so that you get a new model which does not have the information corresponding to the original data point that you want to forget. So let us understand how these contrastive labels can be created and how this neutralized model can be created. So the whole objective is that in the neutralization phase, we would like to forget the information corresponding to the sensitive data set, which is, let us say, represented by a set P. And then what we need to do is like we have to retrain our original model with the mislabeled version corresponding to the sensitive data points. So when we do this, definitely the knowledge regarding the sensitive data point will be lost. So the confidence score will be coming down. But at the same time, the model might lose its utility corresponding to the preservation state. So what will happen? First, it will lower down model's prediction score corresponding to P, but then it might also lose information corresponding to the retail set. So this stopping criteria, as I've said, is like we keep on doing this until and unless training process, until and unless the information corresponding to our forget set or critical data set is close to random guessing. So let's try to quickly understand it. So I have some couple of slides, and after that I will take the questions corresponding to this. So imagine that our whole complete data set, a universe of data set, contains some lakhs of sample, but I am showing here some snapshot, five instances named as X1, which belongs to class 1, X2, which belongs to class 2, and X5, which belongs to class 1. And let us say the private data set, which is represented by set P, is X1 belonging to class 1 until X3 belonging to class 3. So I want to forget all these instances. So the complete data set contains 5 classes, 1, 2, 3, 4, 5. I have just shown a snapshot of 5 instances with 3 classes, 1, 2, 3. And we want to forget instances corresponding to 2 classes, class number 1 and 2. So I want to forget 3 instances, but they belong to 2 different classes. So first objective is to create contrastive label. So we start with an empty matrix of 5 row and 5 columns. And why 5 row and 5 columns? As I said, like I assume that the total number of classes corresponding to my data set is only 5. So I initialize 5 rows and 5 columns. Now what I will do is I have my original model. I take every data point, I present that data point to my model, and I get the output corresponding to all these data points. So let us say if I take sample X, I give it to my original model N, and since it is a 5 class problem, I will get an output like this. If I take data point 2, I give it to the model, I again get 5 different probabilities. So for all 5 data instances, I will get some probability. Now, our job is to forget sample X1, which belongs to class 1, X2 belonging to class 2, X3 belonging to class 1. So what I will try to do is, to the previous matrix, I will try to accumulate the probabilities corresponding to all these instances. So let me start with instance number 2, x2 means this row number 1 belongs to class 1, row number 2 belongs to class 2, row number 5 belongs to class 5. Since x2 belongs to class 2, I will copy the prediction probabilities of this of x2 in this particular matrix, so which is 0 0.1, 0 0.7, 0 0.2. Now, x1 belongs to class 1, so I will go to row number 1. I will copy the value which is 0 0.2, 0 0.5, 0 0.3. Since x3 also belongs to class 1, I will go to row number 1, update the value. So 0 0.4 plus 0 0.2 is 0 0.6, that is why we have 0 0.6 here. 0 0.4 plus 0 0.5 is 0 0.9, it is 0 0.9. And likewise, I will do for the last one, which is 0 0.5. Now, for every row, which is basically a class, I would try to find out the contrastive label. So, contrastive label is a label where the prediction probability is minimum. So, if you traverse row number 1, you'll find that column number 4 and column number 5 is having a minimal value, which means that the contrastive label for class number 1 could be either row number 1, column number 4, or class number 4 or class number 5. Likewise, if I talk about class number 2, which is row number 2, the minimum prediction probability which is again 4 or 5. So we will try to create the contrastive labels corresponding to the class label 1 and class label 2, which we want to forget. Since all other labels like label 3, 4, 5 are not required, we will give it a very high value, which is called as infinite. So what we try to do now is we will make row 3, row 4, row 5 as infinite. So whatever I am speaking is there in the slide. I will share the slides with you, which is called as the remaining set, because I want these classes to be preserved. Now what I will try to do is I want to generate the contrastive label for row number 1. I will try to find out the minimum value. So since there is a tie, I will take the minimum index. So index is 4. So which means the contrastive label for 1 can be 4. You could take 5. You can design the algorithm maybe taking the highest index. So I'm just assuming lowest index. So the contrastive label for class 1, it will be 4. So since 4 is already used, I don't want this 4 to be assigned to class number 2. So I make this particular column as infinite. So what I will do after this, I will update my matrix. I will make it infinite. So for class 1, the contrastive label is 4. Likewise, we will go to row number 2, find out the minimum value. Here the minimum value is 0. So which means for class number 2, the contrastive label is 5. So which now means that all data points which belongs to class number 1 will be relabeled as 4, and all data points which belongs to class number 4 will be relabeled as class number 2 will be relabeled as 5. So now what we do is we will take our preservation step, which says x1 was 1, will be now x1 as 4, x2, let us say it belongs to class number 2, it will be now x2 belongs to class number 5, x3 belongs to class number 1, will be relabeled as x3 as class number 4. So now we will take the contrastive label and we will retrain our model. So we will start with the original model, we will copy the original model. Now what we will do is we will iterate this, we will run the training process until and unless the prediction on the preservation step is next to random. So if you have 110 plus, it should be 1 divided by 10, which is like close to 0.1. So what you do, you take all samples in the preservation set or the sensitive set which had an original label as YP. We train this model, okay, train the copy of the model with the contrastive label, so which we have created previously through our approach, like which is like for 1 which is 4 and for 2 it is 5. And after doing this for some number of times, if we are sure that for all the elements in the preservation set, if the performance is close to next random, so what we do is we will deploy that model as an unlearned model. But I would like to emphasize over here is, since we are doing the training process, it might also have changed the parameters abruptly. So what we now have to do is we have to bring the knowledge, preserve the knowledge corresponding to the retained set. So at this point we will use knowledge distillation. So this model that you have got is a neutralized model which gives you a very low confidence score on the preservation set, but it might also have actually disturbed the performance on the retained set. So how do we try to improve the performance on retained set? What we try to do is we will take our original model which we have saved, which has got the information about the preservation set as well as the retained set. And then what we do, we will take all data points that are belonging to the retained set. We pass it through our original model. We will get the soft labels. We pass the same data to our student model. We will get the soft labels. Now, our job here will be to minimize the output of the soft labels that we got from this neutralized model, which we now call as a student model, as well as from the teacher model. So which means that we want to minimize the distillation loss or the KL divergence, that is output of the student and teacher you want to minimize. But at the same time, what we would also like to do is all the preservation set had their true label. So we will pass, when we pass it to the student model, we would try to compare the soft label. We will take the hard label, the output of the softmax. Okay, we will take the prediction and we will compare with its true label. So effectively what we would like to do is we would also like to minimize the cross entropy loss. So when we do this iteratively, what will happen is we will create a neutralized model which will perform very well on the preservation set and which will give a very less score or confidence score corresponding to the neutralized model. So this model that you get is the unlearned model which you can deploy. So whatever I am saying is also previously we discussed. So effectively what we would like to minimize the KL loss. So which means the distance between the teacher and the student, it has to be minimized. So which can be actually solved through the KL divergence, where Ti and Si is basically the softmax function. And also we would like to minimize the cross entropy loss, that is the difference between the true label and the prediction probability. And then we calculate the total loss, which is alpha times of the cross entropy loss and beta times of the distillation loss. So what we would like to ensure is the classification loss should be minimized so that the student output aligns with the true label, and the distillation loss should be also minimized so that the student mimics the information corresponding to the preservation set from the teacher model. So with this, I would like to stop my lecture because I think it is time, and I'm open to the questions if you have any from my lecture today. Thank you. I think I'm